Hey everybody. Alright, let's see. Now, this should be working. Alright. Hey everybody, how's it going? So, bleh. Sorry we're late. I accidentally updated my, what's going on here? No, okay. I accidentally updated my iPad instead of running the stream. I pressed the wrong button. Whoops. Okay. So this is a stream to kind of go through some extra problems that are similar to the ones in your assignment to kind of give you a clue. I've already had my first visitor of the year who said, hey, there's some stuff on this assignment that you didn't teach us. No. Actually, what they usually say was, hey, we on this assignment, there's stuff we haven't gotten to yet. And that's not quite the case. These assignments always ask you to put what you already know together with some new information. And so, you know, sometimes there's a detail of it that is in the textbook that you haven't maybe paid attention to that I mentioned in class. In class, mostly I've been focusing on the big parts of the calculation, but there's some underlying details here. So yeah, if you feel like you don't know how to start a question, look through the book, come talk to me. It's never as difficult or weird as it seems, but often in these physics classes we put what we've talked about together in new and interesting ways, and in class we can't talk about all the different ways we can put things together. So we're going to start with 22.34, which is actually a question on the assignment. Usually I don't give you questions that are specifically on the assignment. I choose questions that are like the assignment. But with 22.34, oh man. Hold on. The stream. Okay. There's a huge delay in the stream. That's fine. As long as it's healthy, I guess. So what was I saying? Yeah, so this is actually a question on your assignment, and I think it has a few physical details that maybe we didn't elaborate on in class, and also it puts together things that you've done before in class together in new and interesting ways. So I thought we'd do it. Now I'm not going to do the specific one in the textbook, so we're gonna write our own that's fairly similar. So I'll write it right now. Actually, before I do that, let's switch to this paper because I like it more. All right, let's go. Two 3.0 kilogram spheres, and they're small, and they're metal, are hung from nail, a single nail, in the ceiling on 0.25 2.5 meter long wires. I put some excess electrons on each and then touch them together. Afterwards, they hang with an angle of 20 degrees between them. How much charge on each sphere? Okay. How much charge is on each sphere? Question mark. So this is just like the question in the book. It's a two-star question. How do you approach it? So let's talk strategy. This is a static equilibrium question. Okay. The idea being that you have your two balls and they're on these ropes and they're sitting like this. Okay? So they're just sitting in the air and there's 20 degrees between them. Why are they just floating in the air? You know, ordinarily, if there weren't any electric charges on them, you'd expect them to hang like that, touching each other, with no angle between the ropes. But in this case, the angle is 20 degrees. Why is it 20 degrees? And the answer is because there are three forces acting on each of these balls. There's a force of gravity. There's the force of tension in the string. And then there is the electrostatic force, pushing it that way. There's tension, there's gravity, and then there's electrostatic repulsion. Okay? So how large the electrostatic repulsion is depends on a couple things. It depends on the distance between the two, and it also depends on how much charge there is on the two balls. Right? The more charge there is, the stronger they're going to push each other apart, and the larger that angle is going to be. Okay, so the question here is asking about the charges on each of the balls. They're asking for these charges. How do we go about finding them? Are they different amounts of charge? I mean, we talked about in class, even if they are different amounts of charge, these forces that the two charges will feel, the two spheres will feel, those forces are going to be the same because they're equal and opposite, right? So how do we, what's the, I mean, what's the relationship between the amounts of charge on there? Are they different? It seems to me like before I even start this question, I need to address that. And so part of this question comes about with us saying that there are two charges here. Let me find that part of the question. I put excess electrons on each of them and then touch them together. See that particular bit? I put some excess electrons on each of them and then touch them together. What's that all about? That is all about how free electrons move through conductors. Okay? So before we start this question, and this is an this is a static force question, which is to say we're in equilibrium, nothing's moving. We need to find the net force equals 0. That tells you what, hold on. You know that the net force here is equal to 0. You know what the force of gravity is. That tells you what the tension force is. And because you know what the angle is, you can find the electric field force. So we can figure out how much force there is on this. But before we start, let's talk about what this whole sentence I just highlighted is talking about. Okay? If you have metal objects, this one doesn't have very many electrons on it. So I've put a lot of electrons on this one and not very many on this one. those electrons are going to push each other apart on the object. We talked in class about how they're going to be distributed on the surface of it. We're going to talk more about that next week. But the idea here is all these electrons are pushing on each other, and all the electrons in this thing are pushing on each other. And so they'll move as far apart as they can. Oops. When I touch the two together, when you touch the two charged conductors together, these electrons, there's more pressure between them than pressure coming from these guys pushing on them. And so what happens is some of these electrons will migrate to the other charged object until the pressure between the electrons is the same on each of them. So they'll just spread out the way gas does. If you have one room that has a lot of pressure and another room with not very much pressure, and you open a door between them, the gas will move from one room to the other until the pressures are the same. The same thing is working here with these electrons. And since these spheres that we're talking about have the same geometry, they're identical, electrons are gonna move from one to the other until there's the same charge on both of the objects. Okay? And so for that reason, we can assume in our question that there's the same amount of charge on both objects. So that'll make doing it fairly easy, and that's why that particular sentence was in the question. So like I said, this is a question about statics, not static electricity specifically, although that's in it. It's about total force is equal to 0. Okay, so we can calculate each of the forces on the spheres. Let's focus on sphere B. There's a force of gravity. How big is that? It's 3 kilograms, so the force of gravity is 9.81 times 3. So it's going to be minus 29.43 J hat. The force of tension has to cancel that out, so it's going to be plus 29.43 J hat. But I also know, because tension is pointing at a 10-degree angle, that if this vertical component is 29.43, then I can calculate this one using trigonometry. 29.43 times tan of 10 degrees. So that's going to be minus 5.19 I hat. And that means that for all the forces to cancel out, the force from the electric field, the electrostatic repulsion has to be plus 5.19 I hat. Okay? So that's literally a question you could have done last term. You're just talking about the forces all canceling out. Now here's the interesting bit. The interesting bit is us saying, hey, how much charge does it take to make this much force? Well, I know the distance, or rather, I can calculate the distance between these two charges. I can calculate this distance, and I can do it by drawing a triangle. I know that this angle is 20 degrees, and so I can cut this triangle into a right triangle. Okay, so this angle here is 10 degrees. I know that the length of this side is, what did I say? It's 2.5 meters. So this length here, is going to be 2.5 times sine of 10 degrees So it's going to be 0.434 meters. And so this distance between them is going to be twice that on our diagram. 0.868 meters. And what this means is the force here, it's going to be generated by the Coulomb force, K QA QB over R squared. So that's going to be 5.19 newtons is equal to 9E9 QA QB over 0.868 all squared. Distance between them. And now comes the fun part. Like I argued before, because you've touched the two spheres together and they're identical spheres, the amount of charge on each of these will be the same. Q times Q. And so we can solve this equation for Q. 5.19 times 0.868 times 0.868 divided by 9E9 square root answer 2.08 E minus 5 coulombs. And the question asks how many electrons. I guess this is going to be a negative. Why is it going to be negative? These charges have to have the same sign, and it's specified that I was putting electrons on it, so it's probably negative charge. That means electrons. So I was asking how many electrons that took. We know that I'm looking in my book right here. At the start and end of the book, there's always a table of useful notes. Here it is. The charge on electron. One electron has 6 times 10 to the minus 19 coulombs on it. And so the number of electrons is equal to this charge. That's a negative number. Divided by the charge on a single electron. Minus 2.08 E minus 5 divided by minus 1.6 E minus 19. Hmm. 1.3 times 10 to the 14 electrons. And that's how you answer that particular question. All right. So the following questions that I'm going to ask, let's see if anybody's in the live chat. No. I wonder if anybody's watching the thing. Oh, 2 people are watching. Hello. If you have any questions, you can ask them in the live chat, and I will answer them. So let's move on to the next question. .77. I tried to choose questions that were like the ones in the book, and so I'm doing them in an order that I think are similar to the ones on the, I chose questions that are similar to the ones on the assignment. So I'm trying to order them in one that indicates the information on the assignment. So when I do these, it's a good exercise, but it also should give you clues on how to approach the assignment questions. 77 goes this. 3 charged particles are arranged along a line as in figure 2.77. If particle 2 experiences 0 electric force, what's the charge on particle 3? And here's what the particles look like. There's a minus 1, and this one is particle 1. And then there's a plus 1, and that's particle 2. And then over here is particle 3. And this one has minus 4.0 nanocoulombs, and this one has plus 2.0 nanocoulombs, and I don't know what that charge is. So that's the drawing in the book. So it says particle 2 experiences 0 electric force. So we're talking about that one. It says it feels 0 electric force. So how could that be? Oh, also, it's giving me distances here. Let me fill that in before I start analyzing things here. It says this distance here is 10 millimeters, and this distance here is 30 millimeters. All right. So how could particle 2 feel no force? Well, it's feeling a force pulling it to the left from particle 1. So to counteract that, it must be feeling a force pulling it to the right from particle 3, where these two forces have the same magnitude. In other words, particle 3 must be negative. Okay? So they're both attracting. It's pulling them instead of pushing them. It's pulling particle 2 to the left and the right with equal strength, and that's why it feels no force. So it seems like figuring out how much charge there is on particle 3, I need to figure out how much force there is. Wait, hold on. It's supposed to be 3. How much force? I need to figure out how much force that charge is exerting. And figuring out how much force that charge is exerting, I need to figure out how much force is balancing it. So I need to start by figuring out the force from that one on particle 2. And that will then tell me the force exerted by particle 3 on particle 2, which I can then use to figure out how much charge there is. All right, so let's begin. We know that they're we know that they're collinear. They're all along the straight line, along the same line, and so you don't have to work that hard. You don't have to do all that unit vector jazz. You can just insert the vectors by hand. So Q1, Q2, K over R squared. Nanocoulombs. What does nano mean? Let's see. Somewhere out here is a conversion table, I believe. Otherwise, I'll have to ask Google. Oh, here it is at the front of the book. Nano means 10 to the minus 9. So charge 1 has minus 4 times 10 to the minus 9. Particle 2 has 2 times 10 to the minus 9. The Coulomb constant is 9 times 10 to the 9. And the distance between them, careful that you write things in meters. 10 millimeters in meters is 0.1. That's all squared. So that number here is 4. Alright, so it's 7.2 times 10 to the 1, 2, 3, 4, 5, minus 5. So this force here is 7.2 times 10 to the minus 5, and that means this force here pulling it to the right might also be 10.2, right? So force from 3 on 2, it must have the same strength in the positive I-hat direction. So that's equal to Q3 times Q2 times K over, and the distance is 0.03 all squared. So that's, I don't know what Q3 is, but I do know that Q2 is 2 times 10 to the minus 9. I do know that the K is 9 times 10 to the 9, and then that's 0.03 all squared. So I solved that for Q3. 7.2 E minus 5 times 0.03 times divided by 9e minus 9. What? Oh, I see what I did wrong. Okay, here, let me do it again. 7.2e minus 5 times 0.03 times 0.03 divided by 2e minus 9 divided by 9e9. All right. Hold on. There's an issue here with calculators. The first time I made a mistake, don't get me wrong. But there's an issue here with calculators that you might want to keep an eye on. Calculators are sometimes really happy to work in scientific notation, and other times they want to use a decimal expansion, a floating point number, and sometimes they'll convert between the two if they can, because they'd rather display a floating point number than they'd rather display a floating point number. Floating point numbers are just decimal expansions than a scientific notation number. And if they do that, sometimes they'll truncate it. So I just did this calculation and plugged all the numbers in and got 3 times 10 to the minus 9. It dropped the 0.6 because of a truncation error. So just keep an eye out for that when you're plugging things into your calculator. Sometimes you would expect other decimals. It shouldn't just be one number usually. So keep an eye out. In 2.46. Determine the magnitude and direction of the electric force exerted by a 25 nanocoulomb charged particle located at the origin of the Cartesian coordinate system on a 220 nanocoulomb charged particle located at 2,2, drawing and illustrating the various quantities in your calculation. All right. So let's start by drawing the Cartesian coordinate system. Alright, so I'll call that 1. You know what? Let's spread out a little here. I'll call that 1. I'll call that 2. I'll call that 3. 1, 2, 3. All right, so in this question, it's really helpful to draw a picture as you go. Exerted by, okay, so the first one is at the origin. And it's positive, and it's 25 nanocoulombs. 25 times 10 to the minus 9 coulombs. And there's another one, and it's at 2,2, so it's right here, plus, and this one is 20 times 10 to the minus 9 coulombs. All right, so this particular question involves the full strength of all those unit vector things I've been talking about. You don't have to do it that way. I think the book has a way that's a little bit different that you can learn, but you got to learn how to do it. You got to learn how to do it properly. I use unit vectors when I'm explaining it to you guys because there's a lot of basic lessons in learning how to use unit vectors that we've been using all over the place since. But whatever floats your boat. All right. So there's a vector from here to here. I'll call that the R vector, okay? And its components are 2i hat, 2j hat, okay? And this guy's going to feel a force in the same direction. So, according to the steps we talked about in class, first you start with that vector from the one doing the pushing to the one being pushed. Then we find the length of that vector. Square root 2 squared plus 2 squared, that's equal to the square root of 8, which is 2.828 meters. And then the The unit vector is what you get if you take the regular vector and you divide it by its length. So we're shrinking down our original vector so that it's short. How short? We want it to be length 1. 2I hat plus 2j hat. I'm going to show you the intermediate step. So it's 2 over 2.82 I hat plus 2 over 2.828 j hat, which is equal to 0.707 I hat plus 0.707 j hat. So that's my unit vector. And now I'm going to calculate how long this vector is. How strong is that force? And to do that, you need to use one of the ingredients I just found. I just found this ingredient, and I'm going to use that in the calculation of the strength of the force. So the force is going to be QA QB times K over R squared. So that's 25 times 10 to the minus 9 times 20 times 10 to the minus 9 times 9 times 10 to the 9, all divided by the distance between them squared. 2.828 all squared. And you punch those into your calculator. 25e minus 9 times 20e minus 9. Hold on. Times 20e minus 9 times 99 divided by 2.828 all squared. Boop. So that's 5.62 times 10 to the 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 10 to the minus 7 newtons. So I know that the force vector is this long, and I know that it's pointing in the same direction as the unit vector. So to figure out the components of that force vector, I just multiply the strength of the force vector times the components of the unit vector. So that's 3.97 times 10 to the minus 1, 2, 3, 4, 5, 6, 7. I hat plus 3.97 times 10 to the minus 7 j hat. And these are in newtons. Newtons. Okay? And that's how you do that question. Oh, geez. I chose to do so many questions. Well, the more of these you see, the more sense it'll make for you, presumably. 22.61. Still, I got other things I want to do today. Okay, for the charge distribution in this drawing, what is the ratio of the magnitude of the electric force exerted by particle 2 to the magnitude of the electric force exerted by particle 1? By particle 3 on particle 1. Alright, so here's the diagram. This is 1 microcoulomb plus, and this one is minus 4 microcoulombs, and this one here is 2 microcoulombs. This is minus, and this is plus, and this distance here is 50 millimeters, and this distance here is 100 millimeters. Okay, so this question's asking us for the ratio. In other words, let's call these A, B, C, D. Okay, so no, it goes 1, 2, and 3. Okay. So particle 1's going to feel a force from particle 3, and it's going to feel a force from particle 2. And what it's asking us to do is compare the lengths of these two forces. So how do I do that? Well, you don't actually, to answer this question, you don't need to calculate the components of the force, and you already know the length between them. So you just throw it in Coulomb's law. From number 2, that's going to be the charge on it. Okay, micro, let me look it up in the book. Micro, yeah, that's 10 to the minus 6. So that's 1 times 10 to the minus 6 coulombs times 2 times 10 to the minus 6 coulombs times k, all divided by the distance between them. That's 0.1 all squared. So 1e minus 6 times 2e minus 6 times 99 divided by 0.1 times 0.1. So this is 1.8 newtons. Okay. The force, the third force, I'm just going to use different distances, and, you know, it's closer. So it's minus 4 times 10 to the minus 6 times 1 times 10 to the minus 6 times 9 times 10 to the 9 divided by 0.05 all squared. Yep. Okay, so the ratio of F3, I guess that's a negative number, but they're asking us for the ratio, not to compare the numbers, so this ratio, 14.4 divided by 1.8, it's equal to 8. Whoa, why is it a whole number? It's a whole number because when we compare these two formulas, we're using very similar formulas to calculate it. I mean, exactly the same formula to calculate it. So if you compare it, this one is a half this value, and because it's a half squared, this one is going to be twice as big as this one, times 2. This one's going to be 4 times bigger than that one. And then, because, this one and this one, when we compare them, this one is twice as big as this one. This one's going to be an additional multiple of 2 larger than this. So 2 times 2 times 2 is 8. That's fun. All right, 22.55. Cesium chloride is a crystalline salt that forms a cubic lattice structure, which you can imagine as a cube with C+ ions on each of the 8 corners and a C- ion at the center. The edge of the cube is length 412 picometers. Suppose that the edge of the crystal, 2 cesium atoms would be stripped from the adjacent corners of the cube. What is the vector sum of the electric forces exerted by the chlorine ions by the 6 remaining CS ions? Oh my god. Ah, there's an easy way and a hard way to do this. Okay. Which one do I want to use? The easy way or the hard way? There's a medium way. I'll do it the medium way. Okay. So let's start by drawing it. I love drawing pictures of cubes. I don't know if you do, but I totally do. Okay. So, 1, 2, 3, 4, 5, 6. These are all positive. And then there's a negative guy in the middle, right in the middle. And the length here is 412 picometers, which is a ridiculous amount. It's 10 to the 12. So this is 412 times 10 to the minus 12 meters. Okay, how are we going to do this? At face value, I need to calculate 6 different forces. Good news. The nice thing about this is it's symmetric. Okay. Let me name each of these. 1, 2, 3, 4, 5, and 6. Okay. So I need to calculate each of those individual forces and then add them together. There's a nice aspect to this, though. Before we get too big, I'm going to emphasize the strategy we're taking. And the idea here is, because this is in the middle of the cube, each of these is the same distance from the middle. Right? So that's nice. That's going to save us some work. But then additionally, if we think about the vectors and how we're going to break this down into the component vectors, you're going to actually see that there's a really nice pattern. Okay? So, we're going to recognize a pattern. And we're going to take advantage of that. So, let's just do one. Which one? How about number 1? I'm going to try to draw, you know what? 1 isn't the right one. Let's start with number 3. So, there's our positive. Here's our negative. This one's in the center of a great big cube. Okay? And it's actually tough to talk about the center of a big cube, especially in terms of vectors. Well, it's tricky and it's not tricky. We haven't seen too many three-dimensional vectors like this, but I don't know. I saw them a bunch when I was in first year. We break down this R vector in terms of 3 steps. One going along this length. I'll guess that's the I hat length. One going along the J hat length, which points down that way. And then one going straight up in the K hat direction. So it's I hat, which is a right angle, J hat, which is a right angle to that, and then K hat. And those 3 added together give us the overall thing. Okay? And the neat thing is that I know the coefficients of each of these, because it's going to be halfway down each of these lines. 1/2 that distance, 1/2 that distance, 1/2 distance up. And so half of the arc of the length of the side is going to be 206 picometers. 206 picometers. 206 picometers. So even though it's actually pretty difficult to draw and illustrate this particular vector, it's not tricky at all to describe what the components of that vector are. So in this case, it's going to be plus 206 times 10 to the minus 12 meters, I hat, plus 206 times 10 to the minus 12 meters in the j hat direction, plus 206 times 10 to the minus 12 meters in the k hat direction. And now I can just use the same things we did before to figure out how long each of these are. So you can use Pythagoras to figure out how long this is. So 206 e to the minus 12, we're going to square that, times 3 square root. 3.568 times 10 to the minus 10 meters. And this lets us calculate unit vectors, which are just, I'm going to divide this r by its own length, which gives me 206 e minus 12 divided by answer. 0.577 I hat plus 0.5777 j hat plus 0.577 k hat. Now that I know the length and the unit vector, I can figure out how strong the force is. It's going to be, well, positive ions have 1 extra electron worth of charge. Negative electrons have 1 extra electron worth of charge. There's K divided by this distance. 3.568 e minus 10 all squared. All right. So I'm going to look up the charge of an electron. An electron has charge 1.6 times 10 to the minus 19. 1.6 times 10 to the minus 19. 9 times 10 to the 9. Do you think this is going to be a big force or a little force? I don't know. I don't know because they're tiny little charges, but they're quite close together. Alright, one of these is negative. Oh, but I gotta do it again. I got that truncation error I was telling you earlier about. Okay, 1.6 e minus 19 times minus 1.6 e minus 19 times 99 divided by 3.568 e minus 10 divided by 3.568. And you get 1.81 times 10 to the minus 9 newtons. Guess it's going to be a tiny force. That makes sense? They're tiny. Okay, so now we're going to combine this information with this information to figure out the force from 3. Force vector. Minus 1.81 times 0.577. Oh, but 1.81 times 0.577 minus 1.04 10 to the minus 9 I hat minus 1.04 times 10 to the minus 9 j hat minus 1.04 10 to the minus 9 k hat. Okay, so that's the force from one of them. What are we gonna do? That's so much work just for one answer. Do I have to do that again for the other 5? The short answer is yeah, but the medium answer is that you can actually be clever about this and you can make an educated guess. Oops. How is the force from 3 going to differ from the other forces we're talking about? Alright, so you got your charge in the middle. There's our 3. Here is, what did I call that one? I called that one 5. This one's 4. Okay. How do we compare these two forces if you did the calculation? There's that R, first one we just calculated, I'll call it R3. How does it compare with this R, R4? Or this R, R5? The deal here is that they're all, the magnitudes of each of these distances are going to be the same because it's a cube, but the direction they're pointing is going to be slightly different. Okay, so while R3, okay, so I hat's pointing that way, J hat's pointing that way, K hat's pointing up. While R3 pointed in the plus I hat plus J hat plus K hat direction, R4 is going to point in the, let's see, it's still going upwards, plus K hat. It's still going to the right in the positive J hat direction, but now it's going in the negative I hat direction. Okay? So that means the force from 4 is going to be exactly the same as this, but the I hat term is going to switch its sign. Okay. What about R4, R5, R5? What about that one? Well, that one is still pointing upwards, so the still positive K hat. It's moving in the negative I hat direction and the negative J hat direction because it's moving to the left. So force from 4 is equal to, I'm going to switch this sign and this sign. These ones are both going to be negative. So that actually takes us, all right, hold on, 6. 6 is going to move to the right, so it's going to be plus I hat. It's still going to move up, J hat, but it's going to move in the minus J hat direction. Plus 1.04 I hat. Wait, no, minus. It's going to have the same signs, hold on. Same sign as this one, same sign as this one. It's going to flip that sign. Minus, plus, minus 1.04 times 10 to the minus 9 J hat, minus 1.04 K hat. What about these ones on the top? 1 and 2. Well, let's see. That first one, it's going to move along the I hat direction, so positive I hat. It's going to move in the opposite direction of the J hat direction, minus J hat, and it's going to move in the negative K hat because it's going down. So when I switch the signs, I'm going to have to switch the signs of that one and that one. So that's 6f1. It's going to be minus 1.04 blah I hat. It's going to switch this one plus 1.04 blah j hat plus 1.04 k hat. And then the last one going that way, the second charge, it's going in the minus I hat direction. It's going in the minus j hat direction, and it's going down. So I'm going to switch all the signs. Plus 1.04 blah I hat plus 1.04 blah j hat plus 1.04 blah k hat. Okay? So the idea here is that we can use some symmetry arguments to shortcut our way to figure out the form of all these forces. Blah I hat minus 1.04 blah j hat minus 1.04 blah k hat. Okay? And that means that when we add them up, because you know how they have the same magnitude because they're the same distance and the same amounts of charge, and by symmetry you've argued that these are their components, it's really easy to add them up. Why? Because some stuff is going to cancel. I'll do my cancellation with this brown felt pen. So this one and this one cancel out. Hold on, please. This one and this one cancel out. And this one and this one cancel out. Good. So there's no zero I hat term. This one and this one cancel out. This one and this one cancel out, and there's 2 remaining. So it's 2.04 times 10 to the minus 9 j hat. And then on the last one, this one and this one cancel out, and this one and this one cancel out, and so there's 2 remaining, minus 2.04 times 10 to the 9 k hat. All right, hold on, I've got to go get the door. Wait, which class? Physics? From last semester. Okay, well that's got to be it for this. I gotta go now. Sorry. Yeah, this my technical problems at the start ate into this, but essentially this is most of what the questions are asking you calculate. I don't think there's any as weird as this particular one. But the idea here is that sometimes you can use symmetry as a shortcut, which is fun. And we're going to see more and more of it over the course of the term, because physicists are lazy. So anyway, have a nice day. Hold on. Which one was this? This was 55. Oh, hey, we got most of the way through it. All right. So yeah, that's it for today. See ya. Good luck on the assignment.